Hi, in this video, we want to take a look at a case study with regression. All right, so for this case study, we're going to be looking at some sea ice data. There's some issues that come up in this case study that I think is very informative and will help the class understand some aspects of regression that really are not talked about in a textbook sense. Okay, so we're going to be going through an introduction to data science with Python, and here is the textbook's website. What I've got here is a modified version of the code from its website. The textbook is available for available through UCF's libraries to print for free if you're a UCF student. All right, so in our example, first thing we're going to do, we're going to import Seaborn, and I'm pressing F9 as usual. Let's get Matplotlib going. And for this case today, we're just going to do simple linear regression. Easy peasy lemon squeezy. Remember, I have a slope that tells me the rate of change between the predictor variable and the target variable, and we have a y-intercept also. All right, so just to kind of get us warmed up, let's go ahead and use a random number generator to generate some fake data, just so that we can kind of get an idea of what we're doing. All right, so here is a nice little scatter plot with some fake data that was built. And let's go ahead and build a model. And let's go ahead and plot on top of that. So here is our linear regression model. And so as I look through here, I notice that it's a positive slope. And everything's pretty clean, pretty nice. And this is very beautiful data. It's very pretty. There's no issues in this because we generated it and it's fake data. Very much like a textbook data situation. Well, when you go get employed, it's not going to be textbook. So there's going to be some issues that will come up. And let's go ahead and take a look at this case study to find some of those issues. All right, let's go ahead and do another plot. This time we're going to put on a couple different models. Oh, it did not put everything on there like I wanted. Let's do it this way. There we go. Perfect. So here I've got a model going along through here. So this is the one that we generated previously. That's the least squares model. It fits pretty well. Now you'll notice that the green one is almost parallel. It's a little bit bumped above. That could also be a good model to use. It has a good slope estimate, right? Pretty close, but we can see that it's consistently going to predict higher than the observations that we made. And then this one, we can see that this is just a crap model, the yellow one. So ordinary least squares, our goal is to minimize the sum of the square deviations, and that's why we call it least squares. Now, for this case study, we're going to bring in some sea ice data. And we've got some fields in here. We have year, we have month, we have data type, Goddard or NRTSI-G. We have region, this is the hemisphere that the data covers, northern or southern. The extent is the sea ice extent in millions of square kilometers, and then area, sea ice area in millions of square kilometers. Okay. So let's go ahead and get pandas going because we need our data set. So let's go ahead and read in the data. Here's the shape. We see that we have 424 rows of data and 6 columns. And then boom, we've got year, month, data type, region, extent, and area. Well, I use the head attribute to take a look. All right, so now let's do this. Let's go ahead and calculate some means. All right, so we've got year. Okay, the average year is 1996. The average month is 6.5. So let's see, I guess that would be, you know, June or July. I would say probably, yes, that's gonna be, we'll say that's June. And then extent and area are negative. Let's think about that. Think about that for a moment. Extent is the sea ice extent in millions of square kilometers. and area is sea ice area in millions of square kilometers. Do negative numbers make sense? No, they do not. We have a problem. Something's going on. I don't know what the problem is. I need to figure this out. So this is typical of real data, is that you get handed something. You're like, oh boy, it's so great. I'm going to dive in and start working on something. You start working with it, you find that something's wrong. So then you have to figure out what is wrong, how extensively is the problem, and what should I do about it? And how to proceed really is a subjective decision along the way. Real data science is more an art than a science. Okay, so we need to start cleaning our data. So a good thing to do, if you don't know what to do, visualize your data. We think with our eyes. All right, let's go ahead and do a scatter plot. Okay, so let's look at this. Wow, that's a lot of zeros and then 2 negative values. Okay. Now, look at the scale. Look at the scale. So this is 0, negative 10,000. On this scale, these are probably not all 0. Probably. I don't know for certain. They might be. Oh, but they're probably not. They're probably just on this scale, because this is such an extreme number, I can't see that, I can't visually distinguish between the number 0. So these 2 points are causing problems. All right, so what we want to do, we want to find the, we want to find out what's going on with these 2 points. Are these correct? Are these incorrect? Right now, I'm leaning towards there's a problem with these 2 values. What's that problem? I don't know. All right, so our unique values are negative 9999 Goddard NRTSI-G. All right, well, if you remember when we took a look at the data types, it had Goddard NRTSI-G. Okay, so these 2 make perfect sense. Now, what's going on with this one? Well, something that this used to be more common back in the day. Whenever you had a missing value, you would put in something that was just so extremely wrong that the person who received the data would just know this is extremely wrong. This is a missing value. So I suspect, I don't know for certain, I suspect that this negative 9999 is actually the data entry person's way of coding a missing value. They didn't want to leave it blank because there was kind of like a placeholder in the data set, so they put in something else. Usually nowadays we put in maybe an NA, that'd be more common, or N/A if we're working with Excel. Okay, so let's take a look at the values. All right, so we've got 2 entries where the data type is the negative 9999. And when I look at it, got the year 1988 in January, and extent and area both have this extreme missing value. And then in 1987, in December, we have the same values. Okay, so I believe that these are missing values. Even if they're not missing values, these are clearly wrong. So I have to do something about it. Okay, my choices are leave it as is, which clearly is not going to give me what I want because I'll have negative average area. That doesn't make sense. Next one is to try and replace the value with one that I believe is correct. That's called imputation. Or my third value is to kick it out and omit it. The classical statistics point of view is to just omit it. In general, imputation is usually reserved for like machine learning problems, not for statistical inference. All right, so what we want to do, we want to take our data set and keep only the ones that do not have this extreme negative value. And we're going to call that new data set ICE2. All right, so now let's go ahead and plot and see the difference. Okay, so here I've got a bunch of red dots. I can see that the range of the extent goes from 4 to 16, well, a little bit below 4, a little bit above 16. Here, what was going on, these values were so extreme that the 4 to 16 range of values was compressed so small, it just looked like 0 to me. But here we can see that there's kind of like a trend going on. There's overall like a decrease as we go from left to right. All right, so now we want to compute the tendency for a given interval of time that's for a specific month. So we need to normalize the data, and we're going to use the ln plot function from the Seaborn. All right, so let's go ahead and do some plotting. All right, so here, when I take that data and I arrange it by month, I can see that there is clearly a seasonal trend going on. So what we want to do now, we want to take a look at the averages for each of these months. And so what we're going to do, we're going to use the group by. We'll use group by here to group them together. Then when I compute averages on the group by version, what will happen is it will give me the average for each month. All right, so here we can see the average for each month. Okay. So a Carpenter B is not happy with me. All right, so now here's the variance. Now looking through, we have the greatest variability in September. And let's see, when do we have the least variability? Will be in May. That's interesting. Didn't expect that. So May, and so May we have the least variability. And then we get over here, we have the most variability in September. All right, now let's do data normalization. All right, so we can see that we're taking the extent minus the month means and then dividing by the month mean. And that's just a normalize. And let's go ahead and, all right, so now what's going on is that we've made it so that everything's centered at 0, and we can visually see the differences, the deviation from central tendency for each of the individual values. So here in April, this is going to be like this line represents the central tendency for April, and this is, we can see the deviation of our observations from the April central tendency. If I move over to May, the line represents the central tendency of May. I can see the deviation of observations from May's central tendency. I can go down the list. And this gives us a better feel for where we have the spread in our data, where things are tighter. All right, let's see, let's take a look. So the mean is super close to 0, and the variability, when I consider the whole data set, is going to be 32. That's a huge jump. All right, so what's going on is we normalize the data about its month's central tendency, and then so that currently the overall average is 0. And then what we're going to do is when I take the variability, now I've got the variability for the entire data set after I did my normalization, and now that's 32. That's a huge jump from what I had previously. All right, let's plot the entire year. All right, there we go. Now let's look at just January. So here what we're doing is we're building a model just for the January part. And we can do the same for Is that August? Yeah, for August. So this command right here says, hey, I only want the August data because I'm setting the month variable equal to 8. When we do that, we can see it's also decreasing, but something that I kind of want you to notice is that here they look similar, but if you take a second look, you notice, look at the scale on the left-hand side. So -20 to 15, -7.5 to 7.5. These are on 2 different scales. This one is vertically a lot more going on. Since I have these, I'm not using the same aspect ratio on the plots, it's harder to tell that there's a difference with these. It's easy to see that there's a negative trend as we move from left to right, but it's hard to see the magnitude of the slope because I'm using the same plotting scale or same plotting ratio every single time. All right, so let's use some SciPy stats because we are interested in getting some correlation. Okay, so and we can see that we have -0.82 and something that's really close to 0. Or no, sorry, something that's extremely, yeah, that's extremely close to 0. So here we have a correlation of 0.82. All right, so a good rule of thumb is that if you see a correlation less than 0.7, it's not operationally useful. Now, psychologists and academics will tell you that, you know, a correlation corresponds to the amount of variance accounted for, and they'll say a 0.3 is useful. Don't listen to them. Anything less than 0.7 is not useful. I mean, look at the variability on this, and that's with 0.8. I mean, really, like I really can't use this model for reliable predictions, and that's at 0.8. 1 is ideal. So just keep that in the back of your mind as you go out into the world and work with statistics. All right, so let's do some more linear regression. We're going to do regression with year and extent. And we can see that the slope is about -0.5 and the intercept is about 900. Okay. Okay, so now let's go ahead and make a prediction. And let's see, so what we did here is I did some regression. I built a model. And what we're doing is that I'm going to make a prediction with my model. And I'm going to see, hey, does this make a good prediction? Okay, so if I want to use this as a predictive model, I can see the line going through, and I can see it. So look at this vertically. When you look at a point, look at how vertically high or how far above or below the line is vertically. And when I look at it that way, I can see that, you know, it's spread around a bit. So this model really isn't showing strengths for making predictions, but considering I'm only using 1 variable, that's not so bad. Here's our mean squared error of a little bit under 11. Here's our R² score. So this is a correlation between the prediction and the observed of 0.5. That's kind of low. All right, let's do analysis for a particular month. Let's build our model. All right, so here we can see how things go for January for each year. And this time series plots tells us just January. So now let's get the mean squared error, which is a little bit less than 4. And let's get the correlation between the January predictions and the January observations, just a little bit below 0.8. So it's not a great predictive model, but I consider this, to be useful. All right, that's all I've got for you. Tomorrow we'll go over polynomial regression. I hope you're doing well and staying safe. Goodbye.